Hey guys, welcome again to the Maths Club. If you are just joining us, you're welcome. In line with the WAEC syllabus, we're going to continue with a brand new topic, and it's called Surds. I know many of you must have had Surds before. So what exactly is Surds? So Surds are numbers that involve square roots or other roots. So it could be cube roots, it could be fourth roots or anything. And then you cannot express it as a simple fraction or a finite decimal. So let's break down that definition. First is that it has a root. You see that root, I'm sure you know the symbol for root. And then the second thing is that it cannot be expressed as a simple fraction. So you cannot have it like maybe 1 over 2. No, because 1 over 2 is 0.5. But when you have something like 1 over root 2. 1 over root 2, by the time you do it, it has a very, very long value. It could be, take for instance, it could be like maybe 1.32147879. Very, very long. So you can see that it is not finite. Finite means that it has an end. So it cannot be expressed as a finite decimal because it continues on and on and on like that. Now say something that instead they have non-repeating, non-terminating representations as decimals, so just exactly what I just explained. An example of a surd is, you can see root 2. Root 2 is 1.414 and all the way down. Root 3, root 5, root 7. So let me ask, would root 9 be a surd? No, because root 9 is actually a value that is finite, which is 3. So you can see when you have like a value like 3, which is finite, right? Those ones are not really surds. The surds we're talking about here are the ones that cannot be expressed as a simple fraction or finite decimals. They have non-repeating, non-terminating representations as decimals. Let's look at some basic operations that involve surds. The first of it is multiplication. When you have a multiplication of something like square root of 9 times square root of 16, because it's square roots and it's a square roots, you can take the content of both of them and multiply them together. So square root of 9 times square root of 6, you could say, oh, a big square root, and inside that square root you just say 9 times 16. It works. So we have square root of a times square root of b. By the time you see, so we have the big square root, and then see inside the brackets we have a times b. Let's look at an example. So we have the square root of 2 multiplying the square root of 3, because it's square roots and square roots. So you can see that values, which is 2 and 3, we cannot say square root of 2 times square root of 3. Seems like saying square root of big brackets 2 times 3, and 2 times 3 is what? 6. Another example is square root of 5 times square root of 5. Let's solve this one together. So we have square root of 5 multiplying square root of 5. I could put a very big square root and say this is like saying 5 times 5. And 5 times 5 is what? Is 25. And if you look at your maybe calculator or something, if you say square root of 25, that will give you 5. So what do you notice about this? Take a minute and process. What do you notice about this? Great. I can say you actually got it, because if you look at it, when the two values are the same, so if you're trying to find the multiplication of a surd and another surd and they contain the same value, it's just that value. So what am I saying? If I have square root of 7 times square root of 7, without me bothering my head, I know that the answer is just going to be 7, because it's 7 and it's 7. So if I had something like 3 root 2 multiplied by 3 root 2, this is a bit tricky, Abby. I actually put this intentionally. So it's like saying 3 times 3. Let's look at the whole number part. 3 times 3 will give me 9, Abby. Times root 2 times root 2. Root 2 times root 2, because they're the same values. This will give me what? 2. So I don't know, this will give me 18. So what are we saying? Whenever you have something like this, just say 3 times 3, 9. Root 2 times root 2, 2. Because it's the same value. But if it's just singular, like 7 and 7, you don't need to stop at 7. That root 7 times root 7 will give you 7. Root 5 times root 5 will give you 5. But another example, if you had roots 3 times roots 2, just like we had in that previous example, you see they're not the same thing. So if I'm bringing that would be big square roots, and then the content, which is 3 times 2, which is what? Square root of 6. So that's it. Same thing too applies for division. If you have square root of a divided by square root of b, you could as well just group two of them and say a big square root a divided by b. Let's see some examples. Look at this example. We have square root of 35 divided by square root of 5. Let's solve this one together. So we add square root of 35 divided by square root of 5. Because it's square roots and it's square root and it's division that is binding them, you can just say a big square root of 35 divided by 5. Very simple. And 35 divided by 5, we already know that to be 7. So this will be square root of 7. So another example, if I had like square root of 60 divided by square root of 2, I could have just said a big square root of 60 divided by 2. And 60 divided by 2 is what? Is 30. So this answer is square root of 30. Simple and short. Now let's look at addition and subtraction. So the same thing too. You can add or subtract surds only if they have the same radicals. Only if they have the same radicals. So look at it. So look at example is like if they are both square root of 2 or they are both square root of 3. Radicals is this square root of 2 or this square root of 3. Square root of 2 is a radical, square root of 3 is a radical. So let's look at an example of what we're saying. So look at this guy here. You can see they have the same radicals. This square root of 2 and this square root of 2, and we're trying to add them together. So this is like, how many of these guys we have? We have 1 of this root 2. How many of these guys we have? We have 2 of this root 2. If you have 1 of something and you have 2 of something and you add them together, that will give you what? 3 of that thing. Same thing. So these two guys have the same radicals. So this is like you have 5 of root 2. I want to subtract it from 3 of root 2. Of course, 5 minus 3 will give you 2. So that will be 2 root 2. But if you look at this guy here, we have square root of 2 plus square root of 3. Are they the same radicals? No. Right? Because they're not the same radicals, you cannot simplify them any further. You just leave the answer like this. So square root of root 2 plus square root of root 3 is square root of root 2 plus square root of root 3. There is nothing you can do. If we talk about addition, we talk about subtraction, the same law applies to both of them. Now let's look at something interesting called rationalizing the denominator. What does it mean? It's just big English. So you have a fraction a over b or 1 over root 2. It is not always good to have a surd as the denominator, which is the under, right? So if you have 1 over root 2, you might want to simplify it and say, oh, okay, let's look at the way that I'll be able to remove the root 2 from the bottom, but it will still give me the same value. And that's what they call rationalizing the denominator. That's all the big English. So to remove surds from the denominator of a fraction, you can multiply both the numerator, which is the top, and the denominator by the conjugate of the denominator. Let's look at that big English in simple terms. A good example is you have 1 over root 3. Like I said, it's not always good to have a surd as the denominator. So what do? We just multiply the top and the bottom by that denominator. Alright, so you can say 1 over root 3. We multiply the top by root 3 and multiply the bottom by root 3. So 1 times root 3 will give you root 3. And root 3 times root 3, remember what we said in that previous time. Right? So whenever you have root 3 times root 3, it's going to give you 3 without you even solving anything. Because, or if you wanted to solve, you can say square root of 3 times 3. 3 times 3 is 9. Square root of 9 is 3. So if you have a denominator that is a surd, you can rationalize like this. So if I have 1 over 2 root 3, like I said, you can always multiply the numerator and denominator by the denominator. Let's do that together. So you might want to ask yourself, should I use the 2 root 3 or should I use only the root 3? I think to me, anyone that you use, you have the same value. Let's see it. So if I multiply with the top and bottom by 2 root 3, so that is like 2 root 3 all over 2 root 3. 1 times 2 root 3 is 2 root 3. 2 root 3 times 2 root 3 is like 2 root 3 squared, but 2 times 2 is 4 times root 3 times root 3 is 3. So this will give me 2 root 3 all over 12, or I could say root 3 all over 6. Now let's try with only the root 3. So that would be like saying 1 over 2 root 3 multiply the numerator by, instead of saying 2 root 3, we just say root 3 all over root 3. So 1 times root 3 is root 3. 2 times, of course, there is nothing here, but we can assume there is 1, right? We could assume that there is a 1 there. And say 2 times 1 will give me 2 times root 3 times root 3 will give me 3. So it's like saying root 3 all over 2 times 3 is 6. I know this part might be a bit confusing, but you know, when we add 2 root 3 times root 3, we said 2 times 2, 4. Then root 3 times root 3 is 3. If I have root 3, it's like the same thing as saying 1 root 3. So 2 times 1 is 2. Root 3 times root 3 is 3. So you can see that whether we took the entire thing or just took only the root part, we arrived at the same answer. This leads us to something interesting called simplifying expressions. So how can we simplify expressions? Simplifying expressions with surds by combining like terms and applying the rules that we have discussed above. So we're going to combine them by, if it's root 3, we'll combine them together, and then we'll now start applying the rules that we have mentioned previously. Example is root 8. They said root 8 can be simplified to 2 root 2, but how are we going to do this? Let's look at it together. So if I have root 8, to break this down, I'm going to be looking at all the multiple combinations that can give us 8 when we multiply them together, until we find one of them that is a perfect square. So what do I mean by perfect square? 1 squared is 1, 2 squared is 4, 3 squared is 9. So what is 1, 4, 9? They're all called perfect squares. Let's start. The first multiplication that we can get from 8 is 1, 8, which is 8. 1 is the perfect square because 1 times 1 will give me 1, but I'm looking for a perfect square other than 1. So let's go again. We say 2, 4. 2 times 4 will give me 8. You can see 4 is a perfect square because 2 squared will give me 4. So I can just pick out this one and see, instead of me writing 8, I could say square root of 2 times 4. And just like we said, if you have a square root and it's multiplication, remember the rule was saying that if you had square root of A times square root of B, we could have said square root of A times B. Yeah? So we have this part here. I can write it in this way by saying this, like saying square root of 2 times square root of 4. Square root of 4 is 2, so that's saying square root of 2 times 2, and this is the same as saying 2 root 2. So this is how they were able to get the value of 2 root 2 from square root of 8. Also, we are told that square root of 162 can be simplified to 9 root 2. Pause the video and try and see how they were able to get this. Welcome back. Let's look at it together. So if you have square root of 162, what are the combinations that can give us 162? So I could say 1, 162. This gives me 162, but I'm looking for a perfect square other than 1. So let's say 2, 162 divided by 2. If you do it on your calculator, you see that will give you 81. Is 81 a perfect square? Yes, it is, because 9 times 9 will give me 81. So I found my destination. So I could just say this time around, it's always good to put the perfect square first. So you could say square root of 81 multiplied by 2. Just like in the previous example, I could say square root of 81 times square root of 2. Square root of 81 is 9. So this is like saying 9 times root 2, which is equal to 9 root 2. So when you're solving this kind of thing, I would advise that you always put the one that you're going to, the perfect square, first. Unlike that previous example where I put it second. I put it second there. You can see somebody can just say square root of 2. I mean, that could be very funny. But to avoid any form of ambiguity or confusion, always put what you're going to find the perfect square of first. So you can see that's how they're able to get square root of 162 to be 9 root 2. Also, we're told that 3 root 32 can be simplified to 12 root 2. Pause the video and try this one again by yourself. Welcome back. So we had 3 roots 32. I could have broken this root 32. Let's look at how we can break it. We could say 1, 32, 2, what? 16, because 2 times 16 will give me 32. Is 16 a perfect square? Yes, 16 a perfect square because 4 squared will give me 16. So I could write and say this like saying 3 roots 2 times 16. So, I mean, somebody could say, oh, maybe this is like saying 3 root 2 times 3 root 16. No, this is wrong. This is wrong. What you do first is that you factor out that 3. So this is like 3 open brackets root 2 times 16. So that 3 is independent of whatever you're doing inside your brackets. So it's like saying 3 open brackets roots. Okay, I always said you should put this guy first. So let me take my own advice. That's 16 times 2. If I could break this one and say this is 3 open brackets roots 16 times root 2. So this is like saying 3 open brackets root 16 is what's 4. So 4 times root 2. Or this is like saying 3 open brackets 4 root 2. Now I can now multiply that 4 by this 3 that is outside, and 3 times 4 will give me 12. So that will be 12 root 2. So you can see the first sort of mistake that you could make here is by trying to say 3 root 2 times 3 root 16. That is something entirely different. First step is that you factor out the 3, then the root 2 times root 16, you break it up apart. Then when you have found the simplest form, you multiply that, the whole number part, with the whole number that is outside. That will be 3 times 4, and that will give you 12. So the answer is 12 root 2. So that's basically it about this particular subtopic. Now we're going to look at surds in brackets. What does that mean? So just like multiplication. So if you have a surd a plus b, c plus d, the way you do your normal multiplication, you just say a times c plus a times d plus b times c plus b times d. Normal opening of brackets. So for example, we have this guy, 3 root 5 plus 2 multiplying root 5 plus 3, and they give us this answer. Let's now solve it together. So if we're going to be following that format, we're going to be saying 3 root 5 times root 5. So 3 root 5 times root 5 plus 3 root 5 times 3. So 3, let's put them inside the bracket so that we don't confuse anything. So this will be 3 root 5 multiplied by 3 plus 2 times root 5, 2 times root 5 plus 2 times 3. So 2 times 3. 3, I told you, always assume that there's a 1 here. So 3 times 1 is like 3. Root 5 times root 5 is what? Beautiful. 5. Plus 3 times 3 is 9. So root 5 times, is there any other roots? No. So we'll just say 9 root 5. Plus 2 times root 5 is 2 root 5. Plus 2 times 3 is 6. So let's simplify. 3 times 5 is 15. So let me just say this guy would simplify to 15. 9 root 5 plus 2 root 5. You have 9 of something, and you are somebody came again and give it 2 of that thing. So how many are you going to have? I'm going to have 11. So 11 root 5 plus 15 plus 6. 15 plus 6 is what? Is 21. So maybe you might want to write the whole number part first and say 21 plus 11 root 5. Depending on how the answer actually comes. This is how we're able to break down that big thing and come out with a very small thing at the end of the day. And you can see that the answer actually tallies. So we're given this particular one, which is 2 root 2 plus root 5 all squared. I want you to pause the video and try this one out to solve. Welcome back. 2 root 2 plus root 5 all squared, same as saying 2 root 2 plus root 5, close brackets, 2 root 2 plus root 5. I mean, join them with the multiplication. So 2 root 2 times 2 root 2. Let's see. Put them inside the bracket. Plus, this guy will also multiply this guy. This will be 2 root 2 times root 5. Plus, because of space, root 5 times 2 root 2. Plus, root 5 times root 5. So let's now simplify. 2 times 2 will give me 4. So this is 4 times, root 2 times root 2 is 2. No problem. 2 times 1, I mean, you know where the 1 is coming from, is 2. Times root 2 times root 5. We've already said it before that when you have root 2 times root 5, you can see open brackets 2 times 5. 2 times 5 seems like saying 10. So just save me the stress of writing 2 times 5. So let's say that's 10. Plus, this is 1 root 5 times 2 root 5. 1 times 2 is 2. Times square root of root 5 times root 2 is like saying 5 times 2, which is 10, right? Then plus, we have this guy. Root 5 times root 5 is what? 5. So 4 times 2 will give me 8. 8 plus 5 is 13. 13 plus 2 root 2 plus 2 root 2. You have 2 of something and you are going to add another 2 of that thing again. That will give me 4 root 10. So you can see the way we've been able to break this down. Let's see if this thing is actually correct. Yeah, so you can see 13 plus 4 root 10. So just break them apart and use the multiplication of open bracket and close bracket like the way you would do it normally, and you have your answer at the end of the day. It leads us to evaluating expressions with surds. I think that's actually the last session in this particular video. So look at something. This is something very interesting. And it's something that you're going to see in WAEC. This particular question was lifted from WAEC. It's saying that if square root of 1.225 is equal to 1.107, square root of 12.25 is equal to 3.5, and square root of 100 is equal to 10, evaluate square root of 1225. Now, let's see how we're going to actually come up with the solution to this. We know that for our square root of 1225, how can we express it? Can we express in terms of 1.225? And can we express in terms of 12.25? And can we also express in terms of 100? I think using 12.25 and 100 will be easier, because 12.25 times 100 will give me 1225. So I could just come and say something as saying 12.25 multiplied by 100. Abi is the same thing. So I just picked the one that they gave me, because this question is actually saying if this guy is equal to this guy, this guy is equal to this guy, this guy is equal to this guy. I just picked 2 that is very convenient for me. And if this is the case, remember from the law of surds, we could break this apart and say I'm saying square root of 12.25 multiplied by square root of 100, right? We're told that square root of 12.25 is what? 3.5. So let's substitute. That would be 3.5. And we know that square root of 100 is what? 10. So 3.5 times 10 is equal to what? 35. Simple and short. Use what you have to get what you want. So you can see the answer here is 35. And this example is saying that given that 1 over root 2 is equal to 0.7071, and saying by how much is 3 root 2 all over 2 greater than 1 over root 2. This is actually a very interesting question. So we're trying to compare 3 root 2 over 2 and 1 over root 2. If we were trying to resolve this, let's see, if you had 1 over root 2 and I multiplied it by, we're trying to resolve this. This is like saying times root 2 all over root 2. Remember how we said we're going to do this? So this is like saying 1 times root 2 is root 2 all over root 2 times root 2 is 2. So this is like saying root 2 over 2. Right? So 1 over root 2 seems like saying root 2 over 2. So that means that what I could say 3 root 2 over 2, and instead of saying 1 over root 2, I could also say root 2 over 2. We're trying to find out how much this used to be greater than this guy. So it's like saying finding the difference. Now, if you look at this guy, it's like saying 3 times root 2. In fact, let's even factor out. Let's factor out. So we have root 2 over 2. We have root 2 over 2. So I could factor out root 2 over 2 since it's common in both of them. So let's say root 2 over 2. If I factor out this root 2 over 2, what will I have here? I'll have just 3, right? Minus this root 2 over 2. If I remove root 2 over 2 from root 2 over 2, that would just mean what? 1. So this is like saying root 2 over 2. So the difference between two of them is 2 times of root 2 over 2. And we said root 2 over 2 is the same thing as saying 1 over root 2, right? And our 1 over root 2 was 0.7071. So if I now come, I could just say the difference between these guys is equal to 0.7071 multiplied by what? By 2. And if we do that, let's do that together. So this is like saying 0.7071 times 2. So this 2, this 14, 4 carry over 1. 0 times 2 is 0, 1. 2 times 2 is 14, 4.1. 0 times 2 is 0 plus 1. So the answer of this thing is actually 1.4142. So what did we just do? We just use that manipulation that we don't always let to have our surds as denominator. So I try to rationalize it and add root 2 over 2. So anyway, I say 1 over root 2 is like saying root 2 over 2. And if we're trying to find how much 3 root 2 over 2 is greater than 1 over root 2, it's like saying 3 over root 2 minus 1 over root 2. But instead of saying 1 over root 2 now, we now said root 2 over 2. And then we factored out. We factored out root 2 over 2 since it was common in both of them. We're left with 3 minus 1. And we're having 2. And since we're told that 1 over root 2, which seems like saying root 2 over 2 is 0.7071, we just substituted and multiplied and we said, oh, the difference between these two guys is actually 1.4142. If you look at it, that was what they actually had in this particular question. So with this, we've actually touched on so many of the fundamental things about surds. So if you found this video useful, like the video, subscribe to our channel if you have not, comment if you have any question. I will respond to all questions. And one thing I'm willing to know is the more the channel grows, the more I'll be inspired to actually finish up what I started. And I'm sure you will like, if you've been following the videos from the beginning to the end, you realize that we have been putting so much effort from the first topic up to now. So I'll see you guys in the next video. Bye for now.